At full load, the mountain shook hard enough to crack concrete. 30,000 tons of steel, water pressure, and rotating force buried deep inside a hydroelectric cavern were tearing through nearly 1 million gallons of river water every second. The turbine blades spun beneath the mountain like an artificial storm, converting gravity itself into industrial power for entire cities hundreds of miles away. Above the machine, the reservoir looked peaceful. Tourists photographed the water. Children played beside the dam. But underneath that calm surface, the hydraulic monster was feeding. Entire rivers had been redirected into tunnels carved through solid rock. Valleys disappeared beneath reservoirs large enough to drown forests, towns, railways, and ancient roads. Mountains were drilled open from the inside to make room for pressure shafts wider than subway tunnels. Workers blasted through granite for years beneath conditions so dangerous that some projects buried men alive before the turbines ever turned for the first time. Governments called it progress. Engineers called it efficiency. But for the people living near these projects, the machine often felt more like a conquest engine than a power station. Because once the turbines arrived, the landscape itself stopped belonging to the river. The water now belonged to industry. By the middle of the 20th century, these colossal hydraulic systems were powering aluminum plants, electrifying megacities, feeding wartime factories, and transforming nations into industrial superpowers. Some dams produced more energy than entire countries had generated only decades earlier. And the larger the machines became, the more violently they reshaped the world around them. Mountains hollowed from the inside, rivers trapped behind concrete walls, communities erased beneath rising water, all to keep the monster turning. Welcome to History Forged, where forgotten machines, lost industries, and the workers who powered them are brought back to life. Before the hydraulic giants arrived, industrial civilization was running out of strength, not ambition, not manpower. Strength. By the late 19th century, nations were expanding faster than their energy systems could sustain them. Steel mills demanded more electricity. Railways stretched across continents. Mining operations dug deeper into the earth every year. Entire cities were growing upward into forests of concrete and electric light, all of it dependent on machines that consumed impossible quantities of power. And almost all of that power came from burning something. Coal powered the industrial age because humanity had nothing stronger. The mines operated without rest. Men descended underground before dawn, carrying lamps into shafts thick with methane, dust, and collapsing timber supports. Entire regions became blackened landscapes of spoil heaps and smoke. In Britain, Germany, the United States, and Russia, coal trains moved constantly across the countryside, feeding furnaces that never cooled. Factories inhaled mountains. And still it was not enough. The deeper industrial society advanced into electrification, the more unstable the old system became. Steam engines wasted enormous amounts of energy during conversion. Boilers exploded under pressure. Coal transportation consumed entire railway networks simply to keep urban power stations alive. Cities darkened beneath permanent smoke clouds, while workers developed lung disease before middle age. Industrial growth had created an appetite too large for traditional fuel systems to satisfy safely. At the same time, another force remained almost untouched: the rivers. Across North America, Europe, Scandinavia, and parts of Asia, enormous mountain-fed river systems were already carrying tremendous energy, day and night. Snowmelt descended through canyons with enough force to rip trees from hillsides and move boulders heavier than locomotives. Seasonal floods destroyed towns because governments still lacked the engineering power to fully control water at industrial scale. To engineers, this looked like wasted potential. Every descending river represented energy escaping into the sea unused. For centuries, humanity had used primitive water wheels to grind grain or power small workshops, but those systems belonged to a slower world. Industrial civilization required something far larger. Steel production, chemical refining, electric railways, and modern manufacturing demanded continuous power generation on a scale older hydraulic systems could never provide. And the mountains created another problem entirely. Industrial expansion required excavation at unprecedented scale. Railroads needed tunnels blasted through granite. Copper mining expanded into entire mountain ranges. Aluminum refining demanded huge electrical supply systems near remote mineral extraction zones. Nations wanted roads, dams, rail corridors, transmission networks, and industrial cities in terrain once considered almost inaccessible. But mountains resist civilization violently. Before hydraulic excavation systems and large hydroelectric projects, workers relied heavily on manual drilling, explosives, steam-powered compressors, and animal labor. Tunnel crews spent years cutting through rock, one section at a time, beneath conditions that resembled underground warfare. Men operated pneumatic drills for hours in confined darkness, while inhaling stone dust capable of destroying lungs permanently. Some tunnel projects killed workers faster than battlefields. Inside early mountain excavation sites, cave-ins buried crews alive beneath tons of fractured rock. Dynamite misfires detonated without warning. Toxic gases accumulated deep underground where ventilation remained poor. During winter construction, workers blasted through frozen terrain while avalanche conditions surrounded the camps above. And still the industrial world demanded more. More railways, more metals, more electricity, more infrastructure. By the beginning of the 20th century, governments realized that energy and excavation had become connected problems. Modern industry required immense electrical generation capacity, but the best locations for hydroelectric systems often existed deep inside mountainous regions, difficult to access, and even harder to transform. To harness the rivers, engineers first had to conquer the mountains around them. This created one of the largest infrastructure races in industrial history. Entire valleys became future construction zones. Geological surveys mapped river gradients with military precision. Engineers searched for locations where elevation, water volume, and rock stability could support dams large enough to power entire regions. The challenge was terrifying. Hydroelectric systems required more than turbines. They required total environmental transformation. Rivers had to be redirected through tunnels blasted into mountainsides. Pressure shafts needed to descend through solid rock toward underground turbine chambers. Concrete dams had to survive unimaginable hydraulic stress year after year without catastrophic failure. And every additional megawatt demanded larger systems, larger reservoirs, larger tunnels, larger turbines, larger excavation projects. Soon, engineers were designing infrastructure so massive it no longer resembled ordinary construction. Mountains themselves became raw material. Entire peaks were drilled open internally to create hydraulic passage systems capable of feeding colossal turbines hidden underground. The old methods could not keep pace. Steam excavators helped, but mountain terrain often limited mobility. Manual drilling remained painfully slow. Transporting materials into remote valleys required enormous logistical operations involving temporary railways, cable systems, and labor camps isolated from surrounding civilization. Progress became measured in rock removed, and removing rock at industrial scale carried a terrible human cost. Before modern safety standards, excavation crews frequently worked surrounded by unstable geology, while handling explosives powerful enough to collapse entire tunnel sections accidentally. Water seepage turned drilling sites into freezing mud chambers. Ventilation failures filled underground spaces with dust thick enough to blind workers within minutes. Some laborers spent years without ever seeing the completed machine they were helping construct. Because the turbine itself was only the final stage. First came the conquest of the landscape. The industrial world accepted this brutality because the alternative looked worse. Nations that failed to expand power generation risked economic stagnation while competitors industrialized faster. Electricity became tied directly to military production, urban growth, transportation systems, and political power. Hydroelectricity promised something extraordinary. A machine that could feed on gravity itself, no endless coal trains, no furnace smoke, no dependence on imported fuel, just rivers descending through mountains and turbines, extracting nearly limitless industrial power from the motion of water. It sounded almost perfect. But the scale required to make the dream real transformed entire regions into industrial sacrifice zones. Communities living near proposed dam sites often received little warning before relocation plans began. Forests marked for flooding were cleared rapidly. Indigenous lands disappeared beneath reservoir surveys. Ancient valleys that had existed unchanged for centuries suddenly became temporary spaces awaiting submersion. And beneath all of it stood the machine still being imagined. The hydraulic monster. A turbine system so large, so efficient, and so power-hungry that governments were willing to blast apart mountains just to keep it turning. Because industrial civilization had reached a point where controlling nature no longer felt optional. It felt necessary for survival. The hydraulic monster was born from two obsessions: electricity and national power. By the early 1900s, industrial governments understood that the future belonged to nations capable of generating enormous amounts of energy continuously. Coal had built the first industrial empires, but coal also chained those empires to mines, rail transport, smoke, labor unrest, and fuel vulnerability. Entire economies could stall if supply lines collapsed or miners stopped working. Hydroelectricity promised liberation from that dependence. The idea was seductive because the fuel never needed to be transported. The river came to the machine automatically. Engineers across Europe and North America began competing to solve the same question. How could falling water be converted into electricity at truly industrial scale? Earlier turbines already existed, but they were too small, too inefficient, or too unstable for the electrical age now emerging. Then turbine design changed everything. The Francis turbine, developed in the United States during the 19th century, became one of the first systems capable of delivering powerful, reliable rotational energy under varying hydraulic conditions. Water entered the machine under pressure and spiraled through curved blades with carefully controlled flow geometry that minimized wasted force. Efficiency rose dramatically. Soon afterward, Pelton turbines transformed mountain hydroelectric generation entirely. Their split-bucket impulse systems could survive immense water pressure descending from high-altitude reservoirs. Suddenly, steep mountain terrain, once considered an obstacle to industrial expansion, became an advantage. The mountains themselves could now generate power. Then came the Kaplan turbine, capable of adjusting blade angles dynamically during operation. Rivers with changing seasonal flow rates could still maintain high efficiency. This expanded hydroelectric development across entire regions previously considered impractical. By the 1920s, turbine engineering had become geopolitical competition. Nations no longer viewed rivers as natural boundaries. They viewed them as future electrical infrastructure. In the United States, massive hydroelectric expansion accelerated during the Great Depression. The federal government needed employment projects large enough to stabilize collapsing regional economies while modernizing national infrastructure simultaneously. Dams became political symbols as much as engineering projects. Hoover Dam rose from the Black Canyon like a state-built monument to industrial authority. Thousands of workers descended into brutal desert heat to blast diversion tunnels through canyon walls before concrete pouring even began. Entire temporary cities appeared around construction zones because the projects demanded labor forces larger than many military operations. And Hoover was only the beginning. Grand Coulee Dam in Washington state expanded the scale further still. The project required rerouting the Columbia River itself while excavation crews removed millions of cubic yards of earth and rock. Giant conveyor systems operated continuously beside steam shovels and drilling platforms. Concrete pouring became an industrial process, almost as complex as the dam itself. The turbine halls hidden inside these structures were unlike anything humanity had previously built. Generators weighed hundreds of tons, rotors spun beneath ceilings taller than cathedrals, and every additional turbine expanded the industrial capacity of the nation around it. Hydroelectricity became inseparable from aluminum production, wartime manufacturing, and electrified urban expansion. During World War II, dams powered factories producing aircraft, munitions, and industrial materials at extraordinary scale. Entire military economies quietly depended on rivers moving through turbines hidden beneath mountains and concrete walls. The Soviet Union followed the same logic. Projects like the Dnieper hydroelectric station represented ideological statements about industrial modernity and centralized power. Soviet planners viewed river control as proof that the state could dominate geography itself. Gigantic hydroelectric systems became demonstrations of political force visible from miles away. Meanwhile, in Scandinavia, Canada, and parts of South America, governments realized that remote mountain rivers represented enormous untapped economic potential. Regions once considered geographically isolated suddenly became valuable because modern turbines could transform inaccessible terrain into industrial energy networks. The hydraulic monster spread globally because industrial civilization demanded exactly what it provided: massive, uninterrupted electricity. And the larger the systems became, the more profitable they appeared. Large dams created stable reservoirs. Stable reservoirs fed giant turbines continuously. Continuous turbine operation generated enormous electrical output with relatively low long-term fuel cost. The logic became almost irresistible to industrial planners. Why rely entirely on coal shipments when mountains could generate electricity themselves? But the machine required sacrifice before it produced power. Entire valleys had to be transformed into infrastructure corridors. Tunnel systems blasted through granite-connected reservoirs to underground pressure shafts. Rivers were diverted during construction through temporary channels large enough to resemble artificial canyons. Some projects consumed decades. Others consumed landscapes permanently. By the middle of the 20th century, companies specializing in turbine manufacturing had become industrial giants themselves. Firms like Voith, General Electric, Allis-Chalmers, and Hitachi competed for contracts tied directly to national development strategies. The turbine was no longer merely machinery. It had become state infrastructure. Hydraulic engineering also merged with mining expansion during this period. Large hydroelectric systems provided the electricity required for copper extraction, aluminum refining, steel production, and electrified excavation equipment. Entire mountain regions became interconnected industrial ecosystems, where dams powered the destruction of the terrain surrounding them. The contradiction deepened constantly. The same machine marketed as clean energy frequently existed to support some of the most environmentally destructive industries on Earth. And because the turbines became increasingly efficient, governments pursued ever larger projects. Improvements in blade geometry, pressure regulation, cavitation control, and generator design meant more electricity could be extracted from the same river systems. Efficiency created appetite. A slightly better turbine justified a larger dam. A larger dam justified larger reservoirs. Larger reservoirs justified larger excavation operations. Soon, engineers were designing hydroelectric complexes capable of reshaping entire watersheds. Some projects flooded forests so vast they altered regional climates. Others displaced hundreds of thousands of people. Ancient river ecosystems evolved over millennia, vanished beneath artificial lakes, designed entirely around industrial energy extraction. But inside political offices and engineering firms, the calculations still appeared rational. Industrial civilization was expanding too rapidly to slow down. Cities demanded electricity every second. Factories could not stop operating. Transportation systems required stable power grids. Military planners wanted energy independence. The hydraulic monster solved all of those problems simultaneously, and so mountains continued disappearing into tunnels, spillways, penstocks, and underground turbine caverns. Because once nations realized rivers could power modern civilization at continental scale, there was no realistic limit to how aggressively they would pursue hydraulic control. The machine had already proven itself indispensable. Now the world would begin rebuilding landscapes around its hunger. The hydraulic monster lived underground, not because engineers wanted secrecy, but because the machine had become too large, too violent, and too heavy to exist safely anywhere else. Inside mountain hydroelectric complexes, entire caverns were carved deep into granite to contain the turbines. Some chambers stretched longer than battleships and rose several stories high beneath thousands of feet of rock. Overhead, cranes capable of lifting locomotive-sized machinery crawled across steel rails mounted near the ceiling. And beneath the floor, the monster turned continuously. At the center of the system sat the turbine runner itself, a rotating steel structure weighing thousands of tons, forged from hardened stainless alloys designed to survive decades of hydraulic assault. The blades curved outward like enormous metallic claws, shaped through years of fluid dynamics experimentation to extract as much energy as possible from moving water while minimizing turbulence. Every curve mattered. A poorly shaped blade wasted pressure. Wasted pressure meant lost electricity. And lost electricity at this scale meant entire cities losing power. The machine fed on gravity. Far above the turbine hull, reservoirs trapped rivers behind concrete walls hundreds of feet tall. The stored water possessed potential energy created purely through elevation. Engineers called this hydraulic head. The deeper the vertical drop between reservoir and turbine, the greater the pressure generated when water descended. The mountain itself became part of the engine. Water entered giant intake gates positioned behind the dam and moved into pressure tunnels large enough to swallow freight trains. These tunnels, called penstocks, descended through rock toward the turbines below. In major hydroelectric systems, the penstocks could carry millions of gallons of water every minute under crushing pressure loads. Inside the tunnels, the sound became animalistic. The water did not flow quietly. It accelerated through darkness with a deep mechanical roar that shook the surrounding mountain continuously. Workers inside older facilities often described hearing the pressure before feeling it. The vibration traveled through steel platforms, concrete walls, and even the bones inside the body. Then the water struck the turbine. In high-head systems, Pelton turbines operated like industrial artillery. Water emerged from precision nozzles at extreme velocity before slamming into split steel buckets mounted around the turbine wheel. The impact reversed the direction of the water smoothly, transferring enormous momentum into rotational force. At full operation, the machine could spin with terrifying stability. The sound resembled distant thunder trapped underground. France's turbines worked differently. Instead of relying purely on impact force, they used pressure itself as part of the extraction process. Water spiraled inward through adjustable guide vanes before moving across curved runner blades inside enclosed housings. The pressure dropped gradually through the turbine as energy transferred into rotation. The machine did not merely survive the river. It consumed the river's motion piece by piece. Everything inside the turbine hull existed under stress. The rotating shafts connecting the turbines to electrical generators weighed dozens of tons and had to remain perfectly balanced during operation. Even tiny vibrations could become catastrophic over time. Bearings larger than automobile engines supported rotating assemblies moving continuously beneath immense hydraulic load. Heat built everywhere. Generators converted mechanical rotation into electricity through electromagnetic induction. Massive copper windings surrounding spinning magnetic fields produced enormous electrical current, capable of powering entire metropolitan regions. But electrical generation created dangerous thermal buildup. Cooling systems became essential for survival. Water circulated through heat exchangers. Oil systems lubricated bearings constantly. In some facilities, hydrogen cooling systems reduced generator temperatures because ordinary air no longer removed heat efficiently enough at large scale. The smell inside the machine hall became unforgettable. Hot metal, transformer oil, wet concrete, ozone from electrical discharge. And underneath all of it, the mineral smell of river water moving through steel arteries buried inside the mountain. The hydraulic monster never truly stopped moving. Electrical demand changed constantly across the grid. When cities activated factories at dawn, the turbines responded. When millions of homes switched on lights simultaneously at night, the governors inside the station adjusted automatically to maintain precise rotational speed. The machine was reacting to civilization in real time. Control systems monitored pressure continuously because hydraulic imbalance could destroy the station within minutes. If water flow suddenly exceeded safe operational thresholds, turbines could overspeed catastrophically. A runaway turbine spinning beyond design limits could tear itself apart with explosive force, capable of destroying surrounding equipment. And the water pressure itself remained one of the greatest dangers ever harnessed by industrial engineering. Some penstocks operated under pressure loads so enormous that structural failure resembled battlefield detonation. If a major pressure tunnel ruptured, the escaping water could shear through reinforced concrete, collapse walls, and obliterate machinery instantly. The mountain became the containment vessel. That was why engineers buried many hydroelectric stations deep underground. Solid rock provided structural stability impossible to achieve through steel and concrete alone. Entire mountains functioned as armor around the machine. But the machine was also devouring the mountain from within. Excavation never truly ended around major hydroelectric projects. Maintenance tunnels expanded. Additional pressure shafts were drilled. New transmission systems required further blasting through terrain surrounding the station. Some hydroelectric complexes became sprawling underground industrial labyrinths extending for miles beneath the landscape. The mountains slowly hollowed out around the turbines, and the scale kept increasing. By the late 20th century, some hydroelectric systems contained turbines producing more than 700 megawatts each. Single generators weighed thousands of tons. Entire river systems were engineered around maintaining stable flow conditions for the machines hidden below. The hydraulic monster had evolved beyond ordinary infrastructure. It became continental machinery. And despite all its violence, the system achieved something industrial civilization had pursued for generations: extraordinary efficiency. Modern hydroelectric turbines could convert over 90% of the river's energy into usable electricity under ideal conditions. Very little motion was wasted anymore. Almost every ounce of hydraulic force entering the machine emerged as industrial power on the other side. That efficiency transformed the turbines into some of the most valuable machines humanity ever built. But it also created a dangerous illusion. Because the cleaner and quieter the machine appeared, the easier it became to ignore the destruction required to keep it alive. The drowned valleys, the blasted mountains, the displaced communities, the rivers permanently trapped inside industrial systems designed never to release them fully again. By the time the electricity reached the city, all of that violence had already disappeared behind the light switch. The hydraulic monster was sold to the public as a machine of progress, but to the people who built it, operated it, and lived beneath its shadow, the machine often felt closer to a permanent industrial occupation. Because hydroelectric systems did not simply generate electricity, they transformed entire human landscapes. You arrive before dawn. The mountain is still dark above the reservoir, But inside the underground station, the machinery is already alive. It never truly stops. The turbines are turning beneath the floor long before your shift begins, pushing rotational force into generators large enough to power entire regions. The vibration reaches your body first. Not noise, vibration. A deep mechanical pulse moving upward through steel walkways and concrete foundations. Workers inside older hydroelectric stations sometimes spent decades inside this rhythm until their hearing changed permanently. Many operators described carrying the sound home with them after work, feeling phantom vibrations long after leaving the turbine hall. Inside the machine cavern, every surface sweats moisture. Oil hangs in the air beside the smell of heated copper, wet concrete, and river water forced through steel tunnels under impossible pressure. Some stations descended hundreds of feet underground, trapping workers inside environments that felt less like power plants and more like industrial bunkers buried inside the earth. And everywhere around you, the mountain is under stress. The danger inside hydroelectric systems rarely announced itself dramatically. Coal plants exploded visibly. Mines collapsed violently. But hydraulic infrastructure created a quieter kind of fear, because the machine usually appeared calm, moments before catastrophe. A pressure imbalance, a failed bearing, a cracked penstock weld hidden deep inside the rock. That was all it took. When hydraulic systems failed, they failed with overwhelming force. In 1928, the St. Francis Dam in California collapsed catastrophically after structural instability compromised the reservoir wall. More than 12 billion gallons of water erupted through the canyon during the night, obliterating entire communities downstream. Hundreds died beneath floodwater, moving with the force of a moving mountain. The disaster exposed a terrifying truth about hydraulic engineering. Water itself becomes a weapon once industrial systems compress and contain it at large enough scale. Inside hydroelectric stations, workers understood this intimately. Penstocks carrying water toward turbines often operated under crushing internal pressure, capable of tearing steel apart instantly if structural integrity failed. A ruptured pressure shaft could turn a turbine hall into a flood chamber within seconds. And unlike fire, water leaves nowhere to escape. Some workers drowned inside infrastructure they helped build. Others died during tunnel excavation, long before the machines ever generated electricity. Mountain hydroelectric projects consumed labor at extraordinary scale because the terrain itself resisted industrial transformation violently. Tunnel crews blasted through unstable granite while surrounded by toxic dust and explosive gases. Cave-ins buried workers beneath fractured rock deep underground, where rescue operations became almost impossible. Some bodies were never recovered. The mountain simply closed over them. And outside the stations, entire communities disappeared beneath the reservoirs feeding the turbines. Families received relocation notices informing them that valleys where generations had lived would soon become lakes. Forests were cut down before flooding began, leaving ghost landscapes of dead tree stumps protruding from rising water. Cemeteries were relocated, railroads abandoned, churches dismantled. Ancient roads vanished beneath reservoirs designed entirely around industrial energy demand. The machine consumed geography itself. By the middle of the 20th century, hydroelectric systems had become so large that some governments treated rivers as national utility assets rather than ecosystems. Fish migrations collapsed after dams severed spawning routes. Sediment no longer reached downstream farmland because reservoirs trapped it behind concrete barriers. Entire river systems changed temperature, chemistry, and seasonal behavior permanently. And yet the turbines kept spinning, because the industrial world now depended on them. Aluminum refining, electric rail systems, military manufacturing, urban power grids, and eventually digital infrastructure all connected themselves to hydroelectric generation. Entire economies reorganized around the assumption that rivers would continue feeding electricity into civilization indefinitely. Then climate instability began exposing the weakness inside the system. The hydraulic monster depends on predictability, snowpack, rainfall, seasonal meltwater, stable river flow. But modern climate patterns are becoming increasingly violent and erratic. Reservoirs across parts of North America, China, South America, and Europe have dropped to dangerous levels during prolonged droughts. Some hydroelectric stations can no longer operate at full capacity because the rivers feeding them are shrinking. The machine built to dominate nature is now struggling against nature's instability. At the same time, newer energy systems have begun replacing the logic of giant centralized hydroelectric infrastructure. Solar farms, wind networks, battery storage systems, and distributed power grids reduce dependence on singular colossal machines buried inside mountains. But replacement remains incomplete. Because despite everything, the flooded valleys, the blasted mountains, the displaced communities, the environmental collapse surrounding many river systems, hydroelectric turbines remain among the most efficient industrial machines humanity has ever created. Some modern systems convert over 90% of hydraulic energy into electricity. Almost nothing is wasted. That efficiency may be the machine's greatest triumph and its greatest curse, because once civilization discovered how effectively nature itself could be converted into industrial power, the appetite became endless. Rivers became infrastructure. Mountains became excavation sites. Landscapes became engineering calculations. The hydraulic monster taught industrial civilization that even geography could be forced into mechanical service. And today, deep inside mountains across the world, the turbines are still turning. 30,000 tons of steel and pressure hidden beneath concrete and stone, still feeding on gravity, still shaking the earth around them, still powering cities that rarely think about the rivers sacrificed to keep the lights alive.